Picture a vast dark auditorium. You're standing at one end with a flashlight, one of those cheap narrow beam flashlights that throws a bright circle about a meter wide on the far wall. You have been told that somewhere in this auditorium someone is holding up a small sign, and your job is to find it. So you turn on your flashlight and aim it at one spot. You stare at that spot for 30 seconds, no sign. You move the beam to another spot, 30 seconds, no sign. You do this again and again and again, methodically working your way across the darkness, one tiny circle at a time. After an hour, you have checked perhaps 200 spots. The auditorium has 1 million, and you announce to the world that the auditorium is empty. This is, with only slight exaggeration, what SETI has been doing since 1960. The standard approach, the approach used by virtually every major search program from Frank Drake's pioneering Project Ozma to the $100 million Breakthrough Listen initiative, is to point a radio telescope at a single star, listen for a signal for a few minutes or a few hours, and then move on to the next star. If there is a powerful, continuously operating beacon at that star, a cosmic lighthouse blasting energy in all directions, you will hear it. If there is not, you mark that star as a non-detection and proceed to the next one on your list. The assumption buried inside this method is enormous, and almost nobody talks about it. The assumption is that what you're looking for is a civilization so advanced and so energetically profligate that it can afford to operate a permanent omnidirectional beacon, a transmitter that pours energy into space in every direction, 24 hours a day, year after year, century after century, at a power level sufficient to be detectable across thousands of light years. The kind of civilization that could do this would need to command energy resources far beyond anything humanity possesses. It would need the energy output of an entire star. Such civilizations have a name. In 1964, a Soviet astronomer named Nikolai Kardashev proposed a scheme for classifying civilizations based on their energy consumption. A Type I civilization, roughly our level, uses the energy resources available on its home planet. The total power consumption of human civilization today is about 18 terawatts, which is a lot by human standards, but pathetically small by cosmic ones. It is less than 1/10,000th of the energy that the Sun delivers to Earth, which is itself only about 1/2 billionth of the Sun's total luminous output. A Type II civilization in Kardashev's scheme would use the entire energy output of its star, something like 4 × 10 to the 26 watts for a Sun-like star. To put that in perspective, it is roughly 10 trillion times humanity's current energy consumption. A civilization with that much power at its disposal could build an omnidirectional beacon visible across the galaxy. It could disassemble planets and rebuild them as orbital habitats. It could, in principle, construct a shell or swarm of structures around its entire star, capturing every photon and converting it to useful work, a concept that the physicist Freeman Dyson described in 1960 and that bears his name, the Dyson sphere. And a Type III civilization would harness the energy of an entire galaxy, hundreds of billions of stars, all working in concert for the purposes of a single civilization. This is so far beyond any technology we can imagine that it borders on theology. For 60 years, SETI has been looking for Type II civilizations, pointing telescopes at individual stars and listening for their beacons and finding nothing. Here is the question that changes everything. What if Type II civilizations do not exist? What if no civilization anywhere in the galaxy ever reaches that level of energy consumption? Not because it is physically impossible, but because it is unnecessary. What if the path from Type I to Type II is not the natural trajectory of a mature civilization, but a fantasy, an extrapolation error, the kind of mistake you make when you assume that growth curves always keep going up? This is not a fringe idea. It is a hypothesis with a growing number of serious proponents, and it has a devastating implication for how we search, because if there are no Type II civilizations, then there are no omnidirectional beacons, And if there are no omnidirectional beacons, then the strategy we have been using for 60 years is guaranteed to fail. We have been searching for cosmic bonfires in a galaxy that may contain only candles. And candles, from 1,000 light years away, are very difficult to see unless you know exactly where to look and exactly when to look, and you happen to be watching at the precise moment when the candle flame flickers in your direction. This is what the researcher in Siberia understood. And this is why he was looking for something very specific in the TAIGA data, not a steady signal, not a persistent beacon, but a flash. A single, brief, brilliant flash of light lasting less than a microsecond, the kind of flash that a laser could produce. Not just any laser, a laser of a kind that we can already almost build. The physics is clean and specific. Take a laser in the megajoule energy range similar to the ones that already exist at the National Ignition Facility in California, where they are used for fusion research. Give it a pulse duration in the nanosecond range. Focus it through a large optic, not a single mirror, but a phased array of emitters, each one synchronized with the others at the quantum level, so that the whole assembly acts as a single coherent source. With an effective aperture of about 1 kilometer, such a device could produce a beam so tightly focused that for a brief instant, a few billionths of a second, it would outshine its parent star, as seen from any receiving telescope along its line of sight. And here's the critical point. Detecting such a flash does not require a large or expensive instrument. A modest optical telescope equipped with a fast photon counter could pick it up at distances of several thousand light years. The difficulty is not sensitivity. The difficulty is that you do not know when the flash will come or from what direction. It might last 20 nanoseconds. It might come from anywhere in the sky. It might never repeat, or it might not repeat for centuries, depending on how many targets the transmitting civilization is scanning and how long it takes them to cycle back to our star to catch something like that. You cannot point a telescope at one star and wait. You need to watch the entire sky all at once, all the time. You need an omnidirectional detector, which is exactly what the TAIGA cosmic ray array happens to be, not by design. The photomultiplier tubes were placed there to detect Cherenkov flashes from cosmic ray air showers, and they do that job beautifully. But from the standpoint of optical SETI, the array has a remarkable and entirely accidental property. It watches a huge swath of sky simultaneously with nanosecond time resolution, and it can distinguish between events that come from a localized source in the atmosphere and events that arrive as a plane wave from beyond the atmosphere. A cosmic ray shower creates a spreading pool of light on the ground, a pattern that moves and evolves as the shower develops. A laser pulse from a distant star arrives as a flat wavefront, illuminating all the detectors at the same instant. Uniformly, the signatures are completely different. The distinction is unambiguous. So the researcher, his background was in astrophysics, his specialty was SETI, and he had spent years thinking about exactly this kind of problem, wrote new analysis code, applied it to the TAIGA data, and began to search. The first season of data he analyzed was from a single Siberian winter. The observing conditions there are specific and unforgiving. Clear skies come only in the coldest months, when the valley is locked in deep winter and the air is dry and transparent. Summer brings clouds and rain, and no useful data can be collected, so each year's harvest of data is precious and limited. A few months of dark, cold nights. He found several dozen candidate events. Most of them turned out to be something no one had anticipated, a satellite, specifically a satellite equipped with a LiDAR, a downward-pointing laser used to study cloud cover. This satellite was firing nanosecond pulses toward Earth's surface as it passed over the Tonka Valley, and the TAIGA detectors were picking them up. The pulses had exactly the temporal profile, around 20 nanoseconds, and roughly the intensity that one would expect from an interstellar laser signal. They were perfect mimics. This was simultaneously frustrating and exciting. Frustrating because the signals were not extraterrestrial. Exciting because they proved that the detection method worked. The satellite LiDAR was in effect a free calibration source, a laser at a known distance producing a known signal, allowing the researcher to verify that his analysis pipeline was functioning correctly and to characterize the detector's response with a precision that the TAIGA physicists themselves had never achieved. They had been throwing these events away as garbage. He showed them it was gold. But among the dozens of satellite detections and the background of cosmic ray events, there was one candidate that did not fit any known category. It was a repeater, two flashes from the same part of the sky, separated by some interval of time. The positional coincidence was established to, within about a degree, rough but suggestive, two flashes from the same direction, each consistent with a plane wave arrival, each having no match in the satellite catalog or the cosmic ray models. The researcher ran Monte Carlo simulations, computer models that generate millions of fake datasets to estimate how often a coincidence like this would occur by pure chance. The answer came back, about 10%. One time in 10 random cosmic ray events would conspire to mimic exactly this pattern. 10% in everyday life, that would feel like a significant clue. In science, it is nowhere near enough. The threshold for claiming a discovery in physics is typically 5 sigma, a probability of less than 1 in 3.5 million that the result is a fluke. 10% is not 5 sigma, it is not 3 sigma, it is not even 2 sigma. By the standards of rigorous science, 10% is indistinguishable from nothing. The candidate was closed, filed away, not confirmed, not denied, simply left in the liminal space of insufficient evidence, which is where most of the interesting things in science spend their time before they either fade into obscurity or explode into revolution. More data is accumulating, 2 more winters have been recorded, and the analysis is ongoing. Each winter adds more exposure, more statistical power, more chances to catch a flash that arrives at just the right moment from just the right direction and repeats often enough to beat the background. The researcher estimates that the full analysis of all available data will be complete by the end of this year. What it will show, no one yet knows. But even setting aside the specific results, even if every candidate turns out to be a satellite or a cosmic ray coincidence or an instrument glitch, the experiment has demonstrated something that the SETI community has been slow to absorb. It has shown that all-sky optical SETI is not only feasible but already happening, piggybacked on infrastructure built for an entirely different purpose at effectively zero cost. One person, working alone, applying different algorithms to existing data, has achieved an exposure, a product of sky coverage and observing time, that exceeds everything previously accomplished in optical SETI by orders of magnitude. The limitation is coverage. TAIGA watches about 1 steradian of sky, roughly 1/6 of the hemisphere. A complete search would require the full celestial sphere, 2 hemispheres, 12 steradians, 4 pi steradians of total solid angle. You would need multiple arrays at different latitudes or a purpose-built all-sky optical SETI observatory. Such a thing could be constructed. The technology exists. The cost would be a fraction of what was spent on any major space telescope. The question, as always, is whether anyone will write the check. But to understand why anyone should write that check, why the search matters, why it might matter more than almost anything else humanity is currently doing, you need to understand something about the present moment. Not the present moment of SETI research, but the present moment of human civilization. There's a way of looking at the history of life on Earth that reveals a pattern, not a vague hand-wavy pattern, but a specific quantifiable one. If you plot certain measures of complexity against time, the number of species, the maximum body size, the information content of the most complex genome, the energy flow through the biosphere, the curves are not linear. They are not even smoothly exponential. They are punctuated long periods of relative stasis, interrupted by bursts of rapid change, but the bursts themselves are getting closer together. The intervals between major transitions are shrinking. The pace of evolution is accelerating. The emergence of prokaryotic life about 3.8 billion years ago, the emergence of eukaryotic cells about 2 billion years ago, the Cambrian explosion about 540 million years ago, the colonization of land about 470 million years ago, the evolution of mammals about 200 million years ago, the emergence of primates about 65 million years ago, the evolution of Homo sapiens about 300,000 years ago, the agricultural revolution about 10,000 years ago, the industrial revolution about 250 years ago, the information revolution about 50 years ago. Each transition comes faster than the last. If you plot these events on a logarithmic time scale, they fall on a remarkably straight line, a line that, if extended, points toward a moment somewhere in the very near future when the intervals between transitions shrink to zero, a singularity. This is not mysticism, it is an empirical observation. The data points are real, the trend is real. The question is, what happens when the curve reaches its asymptote? There are two broad possibilities. The first is that the curve breaks, that some new transition occurs, so rapid and so fundamental that it makes all previous transitions look gradual by comparison. Perhaps this is the emergence of artificial superintelligence. Perhaps it is the merger of biological and digital consciousness. Perhaps it is something we cannot yet imagine, something that would be to us as we are to the first prokaryotes, so different in kind that the word evolution no longer applies. The second possibility is that the curve does not break, it crashes. The accelerating pace of change overwhelms the adaptive capacity of the civilization driving it, and the whole structure collapses. The technologies that enabled the acceleration, nuclear energy, genetic engineering, artificial intelligence, global communication networks, become the instruments of destruction rather than creation. The civilization does not transcend its limits, it hits them hard and shatters. We are living in the zone where these two possibilities diverge right now, this decade, this century. The curves of exponential growth that have characterized human civilization for the past few centuries are beginning to show the telltale signs of approaching an asymptote. Population growth is slowing, resource extraction is bumping against physical limits. The complexity of our technological systems is outstripping our ability to understand and control them. The list of existential risks, nuclear war, climate disruption, engineered pandemics, unaligned artificial intelligence, grows longer with each passing year, and our mechanisms for managing those risks grow more inadequate. This is not speculation, this is not the doomsaying of pessimists, these are the observed, measured, documented conditions of our present situation. We possess for the first time in our species' history the tools for our own extinction. Whether we also possess the wisdom to avoid using them is an open question, the most important open question in the world. And here finally is why the search for extraterrestrial intelligence is not a luxury. Here is why it is not an indulgence for dreamers, not a hobby for eccentric astronomers, not a waste of resources that could be better spent on earthly problems. Here is why it might be the most important scientific program that our civilization can undertake. If we detect a signal, any signal from any source, carrying any content or no decipherable content at all, we will have learned one thing of absolute transformative importance. We will have learned that it is possible to survive. The logic is precise. Think back to the Drake equation, that famous formula for estimating the number of communicating civilizations in the galaxy. The equation has many factors, most of them uncertain, but they can be grouped into two categories: factors we know and factors we do not. The factors we know are encouraging. The rate of star formation in the Milky Way is about 10 per year. The fraction of stars that have planets is close to 1. We have confirmed more than 5,000 exoplanets as of the latest count, and statistical analyses suggest that planets outnumber stars. The fraction of planetary systems that contain at least one rocky planet in the habitable zone, The orbital band where liquid water could exist on the surface is roughly 1 in 10, perhaps better. Multiply these together and you get a number close to 1. Approximately 1 potentially habitable planet is born in our galaxy every year over the 10 billion year history of the Milky Way. That adds up to billions of opportunities for life to arise, billions of rolls of the cosmic dice. The factors we do not know are, collectively, a single number. The probability that a habitable planet actually produces a communicating civilization. This number folds together all our ignorance about the origin of life, the evolution of intelligence, and the development of technology. It could be 1 in 10, which would mean the galaxy is teeming with civilizations. It could be 1 in a trillion, which would mean we are alone. We genuinely do not know. But here's the insight that makes the Drake equation so revealing and so troubling. Whatever value you assign to the unknown probability, the final answer, the number of civilizations in the galaxy right now, is directly proportional to one more factor. L, the average lifetime of a communicating civilization. Not how long the species survives, but how long it remains in a state where it both possesses advanced technology and has not yet destroyed itself. If L is large, if civilizations typically survive for millions of years after developing radio and lasers and nuclear weapons, then even if the probability of any given planet producing a civilization is tiny, there could be thousands of them in the galaxy at this moment. They would be sparse, separated by thousands of light years, but they would be there. If L is small, if civilizations typically destroy themselves within a few centuries of developing advanced technology, then the galaxy is a graveyard, a place where sparks of intelligence flicker into existence and are snuffed out so quickly that at any given moment there might be only one or none. We know our own L, at least so far. Humanity has possessed the technology for interstellar communication. Radio transmitters powerful enough to be detectable across stellar distances for about a century. We have possessed a technology for self-annihilation, nuclear weapons, for about 80 years. So our L at this point is about 100 years, and counting, the meter is running. Every year we do not destroy ourselves. Our L grows by 1, but what comes next? If we take L to be about 100 years, the duration of the technological explosion we are currently living through, and plug it into the Drake equation, along with the known factors, and even a fairly optimistic value for the unknown probability, the answer is sobering. The expected number of civilizations like ours in the galaxy, civilizations in the middle of their technological explosion, civilizations at our stage of development, is approximately 1. Maybe less than 1. There is one civilization like ours in the Milky Way, and it is us. This does not mean we are alone in the galaxy. It means we are alone at our stage. If there are other civilizations out there, they are either behind us, still in their Stone Age, or their equivalent, or ahead of us. If they are behind us, we cannot detect them. They have no technology, no radio emissions, no lasers. If they are ahead of us, they have passed through the crisis we are now entering and come out the other side. They have survived their technological singularity. Their L is not 100 years, but 100,000 or a million. And this is the key. If we detect a signal from such a civilization, we will know, we will have proof that the singularity is survivable, that there is a path through the fire, that at least one civilization somewhere in the galaxy figured out how to manage the immense power of advanced technology without using it for self-destruction. The content of the signal would matter, of course. If we could decode it, the information might be invaluable. Scientific knowledge, historical records, practical wisdom about how to govern a civilization in possession of world-ending technologies. But even if we could not decode a single symbol, even if the signal were nothing more than a carrier wave with no discernible structure, the mere fact of its existence would carry a message of incalculable importance. It would say someone made it, someone got through. And if they could do it, maybe you can too. It would be like being trapped in a cave system deep underground in total darkness. with your headlamp failing and your air supply dwindling. You have been crawling through tight passages for hours, and you do not know if there's an exit. You do not know if anyone has ever found one. And then faint and far away, you see a glimmer of light. You do not know what the light is. You cannot reach it yet. You do not even know if you could reach it. But you know with absolute certainty that it exists, and that changes everything. That is the difference between despair and hope. That is the difference between giving up and keeping going. The search for extraterrestrial intelligence is, at its core, a search for that glimmer of light. There is another way into this story, and it starts not in Siberia, but in Hawaii, on a mountaintop, on a night in October 2017. The Pan-STARRS telescope sits atop Haleakala, a dormant volcano on the island of Maui, 3,055 meters above sea level. Its primary mission is to survey the sky for near-Earth objects, asteroids and comets, whose orbits bring them close enough to our planet to pose a collision risk. It scans the same patches of sky night after night, looking for things that move against the fixed background of stars. When it finds something new, it flags it for follow-up observations. On October 19, 2017, Pan-STARRS flagged an object that was moving fast. Very fast, too fast. The first thing the astronomers noticed was the trajectory. Every asteroid and comet in our solar system traces an elliptical orbit around the Sun, a closed loop, bound by gravity, repeating endlessly. This object was on a hyperbola. A hyperbola is an open curve, it does not close. An object on a hyperbolic trajectory is not bound to the Sun, it is passing through. It had come from outside the solar system. It was the first interstellar object ever observed. The astronomers named it Oumuamua, a Hawaiian word meaning roughly first distant messenger or scout from far away. They scrambled to observe it with every available instrument before it disappeared back into interstellar space. Because objects on hyperbolic trajectories do not come back. This was a one-time event. Whatever Oumuamua was, they had a few weeks to study it, and then it would be gone forever. The first oddity was its shape, as Oumuamua tumbled through space, rotating once every 7 or 8 hours. Its brightness varied by a factor of about 10. For a solid body, this implies an extreme elongation, a shape roughly 6 to 10 times longer than it is wide. Nothing in our solar system looks like this. Asteroids are typically lumpy and irregular, but they are not shaped like pencils or cigars. The closest analogues in our experience are certain types of icy shards that can form under very specific conditions, but even these rarely achieve axial ratios greater than about 3 to 1. Artist renderings of Oumuamua as a great tumbling cigar of rock became iconic almost overnight, but the shape, however unusual, was not the strangest thing about it. In June 2018, a team of astronomers led by Marco Micheli published a paper in the journal Nature that would transform Oumuamua from a curiosity into a genuine enigma. Using painstaking astrometric measurements, precision tracking of the object's position against the background stars over a period of months, they showed that Oumuamua was not following the trajectory that gravity alone would predict. It was accelerating, not toward the Sun, as gravity would dictate, but away from it. Gently, subtly, but unmistakably, the statistical significance of the anomalous acceleration was 30 standard deviations, a number so high that the probability of it being a measurement error is effectively zero. Something was pushing Oumuamua, something other than gravity. For a comet, this would not be particularly surprising. Comets routinely exhibit non-gravitational accelerations caused by outgassing the evaporation of volatile ices from their surfaces. As the ice sublimates in the heat of the Sun, it forms jets of gas that act like tiny rocket engines, nudging the comet off its purely gravitational path. This is well understood and has been observed for hundreds of comets. But Oumuamua did not look like a comet. There was no coma, no fuzzy halo of gas and dust surrounding the nucleus, which is the defining visual signature of an active comet. The Hubble Space Telescope looked for a coma. The Spitzer Space Telescope looked Ground-based observatories looked. No one found anything. If Oumuamua was outgassing, it was doing so invisibly. This is not impossible. There are theoretical models in which outgassing can occur without producing a detectable coma. For instance, if the volatile material is molecular hydrogen, which is nearly transparent and would dissipate rapidly in the vacuum of space. But these models require exotic compositions that raise their own questions about how such an object could form. The outgassing hypothesis led to a specific prediction about Oumuamua's density. If you know the acceleration and you assume it is caused by recoil from outgassing, you can calculate the rate at which material must be leaving the surface. From that, you can estimate the object's mass, and from the mass and the estimated size, you get the density. The answer, about 1 gram per cubic centimeter, that is the density of water ice, which is plausible for a comet. But it is also much lower than any known asteroid, and it implies that the object is either extremely porous, a fluffy aggregate barely held together by its own gravity, or hollow. There was a second possible explanation for the anomalous acceleration, and it led to an even more provocative conclusion. Sunlight carries momentum. When photons strike a surface, they exert a pressure, a tiny force, but a real one. For most objects in space, solar radiation pressure is negligible compared to gravity. A boulder does not get pushed around by sunlight, but a very thin, very lightweight object, an object with a large surface area relative to its mass, can be significantly accelerated by radiation pressure. If solar radiation pressure was responsible for Oumuamua's anomalous acceleration, the required surface-to-mass ratio can be calculated precisely. The answer, about 1 gram per square centimeter. This is the surface density of a sheet of aluminum foil, or a thin plastic film, or a solar sail. The Harvard astrophysicist Avi Loeb was the first to point this out in a peer-reviewed paper, and the response from the astronomical community was immediate and largely hostile. Loeb was accused of sensationalism, of jumping to conclusions, of violating the scientific norm against invoking extraordinary explanations when ordinary ones have not been exhausted. The criticism was not entirely unfair. Loeb has a flair for publicity that rubs some of his colleagues the wrong way. But the scientific substance of his argument was harder to dismiss than the tone of the objections might suggest. Because here's the thing, we have a direct comparison case. In 2020, astronomers discovered another object exhibiting anomalous acceleration due to solar radiation pressure. It was designated 2020 SO, and its orbit was unusual. It appeared to be temporarily captured by Earth's gravity, looping around our planet before drifting away again. When orbital dynamicists traced its trajectory backward in time, they discovered something remarkable. 2020 SO was not a natural object. It was the upper stage of an Atlas Centaur rocket that had launched the Surveyor 2 spacecraft toward the Moon in September 1966. A hollow metal cylinder, thin-walled and lightweight, tumbling through space for 54 years before being recaptured by Earth's gravity. Its behavior was virtually identical to Oumuamua's, the same anomalous acceleration, the same response to solar radiation pressure, the same implied surface density, a thin, lightweight, hollow structure pushed around by sunlight like a leaf in a breeze. Two objects, same behavior. One is confirmed space junk, an artifact of human technology, a discarded rocket stage. The other is unknown. This does not prove that Oumuamua is an artificial object. The comparison is suggestive, not conclusive. There could be natural mechanisms that produce thin, lightweight interstellar objects, fragments of planetary crust shattered by collisions, for example, or sheets of nitrogen ice carved from the surface of a Pluto-like world in some distant planetary system. These explanations have been proposed, and some of them are plausible, but none of them are without difficulties. And all of them require assumptions that are at least as exotic as the hypothesis that Oumuamua is a piece of technology. There is one more detail worth noting, and it concerns the velocity at which Oumuamua entered our solar system. Its speed relative to the Sun was about 26 kilometers per second. This number has a specific meaning in galactic dynamics. It is the typical peculiar velocity of stars in the solar neighborhood, the speed at which stars drift relative to one another as they orbit the center of the galaxy. An object that was gently released from a planetary system dropped into interstellar space at negligible velocity, like a bottle tossed from a ship, would drift through the galaxy at this characteristic speed, carried by the motion of its parent star. Oumuamua arrived at exactly this speed. It did not come in fast like something fired from a cannon. It drifted in like something that had been floating for a very long time, perhaps millions of years, perhaps billions, floating through the emptiness between stars, occasionally passing through a planetary system, pulled briefly into a hyperbolic orbit by the star's gravity, and then drifting on. If Oumuamua is indeed an artifact, a piece of a solar sail, a fragment of a defunct spacecraft, a shard of a structure built by someone who is no longer there, then its story is not one of deliberate contact. It is a story of cosmic litter, galactic flotsam, something that was used and discarded and forgotten countless ages ago by beings who may themselves be long gone. And then, after eons of silent drifting, it happened to pass through our solar system at the exact moment in cosmic history when we had just barely developed the ability to notice it. The poignancy of this possibility is hard to overstate. We may have been visited by an artifact of another civilization, not a message, not a probe, not a deliberate act of contact, but a piece of garbage, a bottle that no one threw, a note that no one wrote. And we saw it for a few weeks, took some blurry pictures and watched it disappear forever into the dark. Could we have done more? Could we catch it? Mission studies have been conducted, and the answer is possibly, with current technology, a spacecraft launched on a carefully designed trajectory using gravitational slingshots around Venus and the Sun to build up velocity could theoretically intercept Oumuamua. The journey would take about 10 years. The cost would be significant but not prohibitive, well within the budget of a medium-class space mission. Several detailed mission architectures have been published, none have been funded. 10 years from now, Oumuamua will be even farther away, and the launch window will have closed, the opportunity will be gone, and we will never know what it was unless another one comes along, and the statistics suggest that they do regularly. Oumuamua was the first interstellar object we detected, but it was almost certainly not the first to pass through our solar system. Our surveys have simply not been sensitive enough to spot them until very recently. As our telescopes improve, we are likely to find more, perhaps many more. Each one will be a message in a bottle from beyond our solar system, whether or not anyone intended it to be. Now let me take you somewhere else, not to Siberia, not to Hawaii, but to a room. A quiet, climate-controlled room in a university somewhere, where a person is sitting in front of a whiteboard covered in equations. The equations describe something that does not yet exist and may never exist. They describe a network, a galaxy-spanning web of information, passed from civilization to civilization across thousands of light years, accumulating over millions of years, carrying within it the collective knowledge and cultural heritage of every species that has ever achieved the ability to communicate across the stars. The model is called the galactic cultural field, and it is the kind of idea that makes serious scientists nervous, because it sounds like science fiction, and in some ways it is. But it is science fiction with a mathematical backbone, and the mathematics produces results that are specific, testable, and surprising. The starting premise is this: suppose that a civilization survives its technological singularity. It passes through the crisis zone, the period of maximum danger, when it possesses the power to destroy itself but has not yet developed the wisdom to reliably refrain, and emerges on the other side. What is it like now? The model makes a specific prediction about the psychology of such a civilization, and it derives this prediction from a kind of evolutionary argument. The argument goes, Any civilization that survives the singularity must have developed certain psychological or cultural traits that enabled its survival. Foremost among these would be what you might call an altruistic imperative, a deep, structurally embedded commitment to cooperation, long-term thinking, and concern for the welfare of others. Not because altruism is morally superior, though it may be, but because civilizations that lack it destroy themselves. The singularity is a filter. Only the altruists get through. If this is true, then a post-singularity civilization would naturally be inclined to share its knowledge, not for any expectation of return. The light travel times are too long for any meaningful dialogue, but as an act of generosity, a paying forward, a casting of seeds into the cosmic wind in the hope that some of them somewhere will find fertile ground, such a civilization would transmit. It would encode its accumulated knowledge, its science, its history, its art, its hard-won understanding of how to survive, and beam it into space, targeted at stars where habitable planets might exist. The transmission would be continuous, or at least regular, and it would be designed to be as easy to detect and decode as possible. A calling card of prime numbers, perhaps, followed by a mathematical primer, followed by progressively more complex information, building up from elementary concepts to advanced knowledge in a self-contained, self-teaching curriculum. Now suppose there are several such civilizations in the galaxy. Each one is transmitting independently, beaming its accumulated knowledge into the void. Eventually, some of them will detect each other's transmissions. And when a civilization receives information from another civilization, something interesting happens. First, it incorporates the new information into its own knowledge base. Alien science, alien biology, alien history. All of it is novel, all of it is potentially useful, and some of it might be transformative. The receiving civilization becomes wiser, more capable, better equipped to survive whatever challenges it faces. Second, and this is the crucial step, it retransmits not just its own knowledge, but everything it has received from others, added to its own contributions. The next civilization to receive its signal gets not one civilization's worth of knowledge, but two, and when that civilization retransmits, the signal contains three civilizations' worth of knowledge, and so on. The information does not stay in one place. It bounces from civilization to civilization across the galaxy like a ping-pong ball, accumulating new content with each bounce. Over time, the total volume of circulating information grows without bound. Every civilization that participates in the network gains access to the entire accumulated heritage of every civilization that has ever contributed to it. The galaxy becomes, in effect, a library, a vast distributed self-replicating library, with each participating civilization serving as both reader and librarian. The mathematical analysis of this model reveals something unexpected. There is a critical threshold, a minimum density of civilizations in the galaxy, below which the network is sparse and fragile, with isolated nodes flickering in and out of existence, too quickly to sustain a stable web of information exchange. But above that threshold, the system undergoes a phase transition. The network becomes self-sustaining. It grows, not linearly, but explosively, a positive feedback loop in which increased information flow leads to increased civilizational longevity, which leads to increased reach, which leads to increased information flow. The time scale for this phase transition is on the order of the lifetime of a single civilization. Which means that if the galaxy has crossed the threshold, if there are enough communicating civilizations to sustain the network, then the galactic cultural field already exists. The information is already out there, washing over us like cosmic background radiation, filling the space between stars with the accumulated wisdom of 1,000,000 worlds. And we have no idea. We have not built the receivers. We have not listened. We are standing in a room full of music and we cannot hear it because we have not yet invented ears. Or maybe not. Maybe the threshold has not been crossed. Maybe the network does not exist. Maybe we are alone, or nearly so. and the galaxy is silent. This is also possible, and the model cannot distinguish between the two scenarios without observational data, which brings us back, as always, to the need to search. But suppose, just for a moment, that the network exists. Suppose that somewhere in the sky right now, a signal is arriving, a signal that contains not just the knowledge of one civilization, but the compressed, accumulated heritage of thousands. Suppose that within that signal is the answer to every question that haunts us: how to generate energy without destroying our climate, how to cure diseases we have not yet identified, how to structure a society that is both just and sustainable, how to manage technologies of godlike power without using them for self-destruction. Suppose that all of this is there, encoded in pulses of light or radio waves streaming past the Earth at the speed of light, and all we need to do is build a telescope and tune it to the right frequency and point it in the right direction and listen. Would we do it? The cost would be trivial. A purpose-built all-sky SETI observatory, covering both radio and optical wavelengths with sufficient sensitivity to detect Type I civilization signals at distances of a few thousand light years, could be built for less than the cost of a single modern fighter aircraft. The technology exists, the scientific justification is clear, the potential payoff is not merely large, but literally incalculable. And yet, the history of SETI funding is a history of false starts, political ridicule, and chronic underfunding. NASA's most ambitious SETI program, the High Resolution Microwave Survey, was killed by Congress in 1993 after less than a year of operation, torpedoed by a senator who declared that not a single Martian has sent us a message. The entire field has survived largely on private donations, supplemented by the creative repurposing of instruments built for other purposes, like the cosmic ray detector in the Tunka Valley. The irony is exquisite. We spend hundreds of billions of dollars each year on weapons designed to protect us from threats that are, in the cosmic scheme of things, trivially local. We spend tens of billions on entertainment, on movies and games and streaming services designed to help us forget, for a few hours, the anxiety of being alive in a dangerous world. And we spend almost nothing, a few $1 million a year globally, on the one program that could tell us whether our species has a future. There is a Chinese science fiction novel. It has sold millions of copies worldwide and has been adapted into a major TV series that offers a very different perspective on the question of extraterrestrial contact. The novel is called The Dark Forest, and it is the second volume of a trilogy by the writer Liu Cixin. Its central idea is simple, elegant, and terrifying. The galaxy, Liu argues, is like a dark forest. Every civilization is a hunter moving silently through the trees, rifle in hand. No one speaks, no one calls out, because in the dark forest, any noise you make could attract the attention of another hunter, and that hunter's first and most rational response will be to shoot you, not out of malice, but out of self-preservation. You do not know the other hunter's intentions, you do not know whether they are peaceful or aggressive, and the cost of guessing wrong is extinction. So you shoot first. You always shoot first, and the forest stays dark and silent, because everyone who ever called out is dead. This is Liu's answer to the Fermi paradox, the famous question posed by the physicist Enrico Fermi in 1950 about why we have not detected any evidence of extraterrestrial civilizations despite the apparent probability that they should exist. The answer in Liu's telling is that they are out there, but they are hiding from each other and from us. The dark forest hypothesis has generated enormous discussion, both among science fiction fans and among working scientists. It is elegantly argued, and it taps into a deep and very human anxiety about the nature of the unknown. But when you examine it closely, it contains two significant logical flaws, and understanding those flaws reveals something important about the actual risks and the actual promise of searching for extraterrestrial intelligence. The first flaw concerns the premise of hiding. Liu's argument assumes that civilizations can protect themselves by remaining silent, by not transmitting, by not revealing their existence. But this assumption ignores the enormous asymmetry in capability between the civilizations that could actually threaten us and the civilizations we might need to hide from. Any civilization capable of projecting destructive force across interstellar distances, sending a fleet of warships, or launching a relativistic kill vehicle, or whatever other mechanism of annihilation you care to imagine, would, by definition, be vastly more advanced than we are. It would be a Kardashev Type II civilization at minimum, with energy resources millions of times greater than ours. And a civilization with that kind of energy at its disposal would have no difficulty building space-based antenna arrays with apertures of 50 kilometers or more. Such arrays exist in concept, and there is nothing in physics that prevents their construction. And with such instruments, detecting Earth would be trivial, not because we are deliberately broadcasting, though we are, in the form of radar emissions and TV signals and the electromagnetic leakage of our entire technological infrastructure, but because our military and airport radars operate at high power levels and very specific frequencies that are unlike anything produced by natural processors. To a sufficiently sensitive receiver, Earth is a beacon, a glowing, screaming, unmistakable beacon advertising our presence to anyone within several thousand light years who has the technology to look. We have been broadcasting since the late 1930s. That signal sphere is now about 170 light years in diameter and growing. There is no way to recall it. There is no way to hide, which means that if there are predator civilizations out there, civilizations with both the means and the motivation to destroy us, they already know we are here, or they will know as soon as our expanding sphere of radio emissions reaches them. Hiding is not an option. The decision to reveal ourselves was made for us, involuntarily, by the engineers who built the first high-power radar systems during World War II. We cannot undo it, we cannot take it back. We are visible whether we like it or not, so the question of whether to search for signals and whether to transmit signals is moot from a security standpoint. The damage, if there is any damage, is already done. We might as well listen. The second flaw in the dark forest hypothesis is more subtle but equally devastating. It concerns the question of motivation. Why would an advanced civilization bother to destroy a primitive one? Liu's answer is that even a primitive civilization might eventually become a threat, that the only way to guarantee your own safety is to eliminate all potential competitors before they develop the capacity to harm you. This is the logic of preemptive strikes extended to the cosmic scale. But this logic ignores a far simpler and more effective strategy for ensuring your own survival: dispersal, a civilization that can travel between stars, which is, remember, the prerequisite for being able to attack other civilizations across interstellar distances, can also colonize multiple star systems. A civilization spread across dozens or hundreds of worlds is effectively invulnerable. No single attack, no matter how devastating, can destroy all of its outposts simultaneously. The vast distances between stars which make interstellar warfare so difficult also make interstellar genocide essentially impossible. You would have to find and destroy every single colony in every single star system, and there could be hundreds of them scattered across thousands of light years. A rational civilization, upon developing interstellar travel capability, would immediately begin to disperse, not out of fear, but out of simple prudence. The same impulse that drives humans to back up their hard drives would drive an advanced civilization to back up its species. Spread out, diversify. Do not keep all your eggs in one basket. This is not altruism, it is enlightened self-interest, and a civilization that has successfully dispersed has no reason to fear anyone. It is, for all practical purposes, indestructible. The dark forest logic, the imperative to shoot first, evaporates. If you cannot be killed, you have no reason to kill. The dark forest becomes merely a dark garden, and you can afford to be curious about the other gardeners. There is a testable prediction buried in this argument, and it strikes at the heart of the dark forest hypothesis. If the first civilization to arise in the galaxy had adopted the dark forest strategy, if it had set out to destroy or prevent all other civilizations, it would have targeted the most promising planets first, the planets most likely to produce intelligent life, the ones with stable stars, rocky surfaces, liquid water, and favorable positions within the galaxy, away from the turbulent core, away from the spiral arms where supernovae are common in the quiet, comfortable suburbs of the Milky Way, planets, in other words, exactly like Earth, orbiting stars exactly like the Sun, in galactic neighborhoods exactly like ours. If the dark forest is real, we should not exist. Our planet is one of the most favorable locations in the galaxy for the emergence of intelligent life. If anyone was going around sterilizing promising worlds, Earth would have been near the top of the list. The fact that we are here, the fact that intelligent life arose on one of the best possible planets in one of the best possible locations, is strong evidence that no one is doing that. Either there are no dark forest predators, or they do not follow the logic that Liu ascribes to them, or they do not yet exist. Any of these conclusions undermines the case for hiding. When Liu Cixin was asked about this argument in a private conversation, asked directly whether his dark forest hypothesis should be taken seriously as a guide to policy, he reportedly responded with a straight face, "It is fiction." I was joking. And then, after a pause, he added, "I think we are alone in the galaxy." He did not elaborate. Whether he truly believes this is impossible to say, but the remark highlights something important about the relationship between science and science fiction in this domain. The dark forest hypothesis is a powerful narrative device. It generates suspense, it raises the stakes, it forces characters to make agonizing decisions. It is brilliant fiction. It is also, as an actual model of galactic sociology, almost certainly wrong. And the reasons it is wrong are themselves scientifically interesting because they tell us something about the constraints that physics and game theory place on the behavior of civilizations. But there is one aspect of Liu's trilogy that deserves to be taken seriously because it points to a genuine risk that the SETI community has not adequately addressed. This is the risk of information warfare. In the novel Contact by Carl Sagan, a very different kind of first contact story, warmer and more optimistic than Liu's humanity, receives a message from an advanced civilization. The message contains what appear to be the blueprints for a machine. The machine is built, people climb inside it, they press the button. The novel treats this as a hopeful, transformative event, but from a security standpoint, it is insane. Building and activating an unknown device of alien design without fully understanding how it works or what it will do is the extraterrestrial equivalent of running an email attachment from an unknown sender. It is the kind of thing that no responsible civilization should ever do, and yet the novel's scenario, stripped of its dramatic trappings, points to a real possibility. What if an advanced civilization transmits not just information, but executable code? What if the message contains a program, an algorithm, a set of instructions, something designed to be run on whatever computational infrastructure the recipient possesses? The code might be presented as a gift, a miraculous technology, a solution to some pressing problem, a key to vast stores of additional knowledge. The temptation to run it would be enormous, and the code might not be what it seems. It might be a virus, a piece of self-replicating software designed to take over the recipient's infrastructure, to reshape their civilization in the image of the sender, to achieve by information what could not be achieved by force, a virtual colonization, a conquest at the speed of light. This scenario is speculative, and there are reasons to doubt it, the most obvious being that the sending civilization would need to know the recipient's computational architecture in advance, which seems unlikely for a first contact, but it illustrates a general principle that the SETI community needs to take seriously. Receiving a message is not the same as understanding it, and understanding it is not the same as being able to use it safely. The appropriate response to an extraterrestrial signal is not to run its contents, but to study them carefully, methodically, in isolation from critical infrastructure, for as long as it takes to understand what they are and what they do. This is, of course, exactly what responsible scientists would do. The concern is that not everyone who might gain access to an extraterrestrial signal would be a responsible scientist. In a world of globally interconnected information systems where data can be copied and distributed in seconds, controlling access to a decoded alien message would be extraordinarily difficult. And in a world that contains not just responsible scientists but also reckless hackers, messianic cults, and authoritarian governments, the potential for misuse is real. This is not an argument against searching. It is an argument for thinking carefully about what we will do when, if we find something. It is an argument for developing protocols and safeguards in advance before the signal arrives, while we still have the luxury of time and calm deliberation. The SETI community has in fact developed such protocols, a set of guidelines known as the Declaration of Principles Concerning Activities, following the detection of extraterrestrial intelligence adopted by the International Academy of Astronautics. But these guidelines are voluntary, unenforceable, and largely unknown outside the small community of researchers who drafted them. They are a starting point, not a solution. The deeper point is this: the question of what to do with an extraterrestrial signal is not a scientific question. It is a political, ethical, and philosophical question. A question about the governance of knowledge, the management of risk, and the distribution of power in a global civilization that is already struggling to manage the technologies it has invented for itself. Adding alien technology to the mix could be either a salvation or a catastrophe, and which one it turns out to be will depend not on the nature of the technology, but on the nature of the civilization that receives it. Which brings us back, once again, to ourselves. There's a pattern in the history of science that reveals itself over and over so consistently that it might almost be called a law. Every time we look outward, every time we study something distant and alien, something beyond our immediate experience, we end up learning something important about ourselves. Copernicus looked at the planets and discovered that the Earth is not the center of the universe. Darwin looked at the variety of life and discovered that humans are not separate from nature but part of it. Hubble looked at the galaxies and discovered that the universe is expanding, that it had a beginning, that everything we see is part of a vast cosmic story that started 13.8 billion years ago and is still unfolding. Each of these discoveries was a blow to human vanity. Each one made us smaller in the cosmic scheme of things, and each one paradoxically made us wiser. Not by giving us new technologies or new sources of power, but by giving us a more accurate picture of our situation, a clearer understanding of where we are, and what our options might be. The search for extraterrestrial intelligence is the next chapter in this story, whether we find anything or not. The search itself is transformative because it forces us to confront questions that we would otherwise avoid. Questions about the long-term viability of technological civilizations. Questions about the nature of intelligence and whether it is a universal property of complex systems or a cosmic accident. Questions about the relationship between knowledge and power, between capability and wisdom, between the ability to destroy and the choice not to. These are not abstract philosophical questions. They are practical questions with immediate relevance to the survival of our species. And the fact that they arise naturally from the search for extraterrestrial intelligence, that the same program of research that might discover cosmic neighbors also sheds light on our own existential predicament, is not a coincidence. It is a reflection of the deep unity of knowledge, the fact that understanding any part of the universe helps us understand every other part, including ourselves. Let me tell you about one more piece of the puzzle, because it addresses a question that has been hovering in the background of everything we have discussed, the question of convergence. When we search for extraterrestrial signals, we make assumptions, usually implicit, rarely examined, about the nature of the intelligence that might be producing them. We assume that alien civilizations would use radio waves or lasers to communicate, because these are the communication technologies we have developed. We assume that they would encode their messages using mathematics, because mathematics is the language we use to describe the physical world. We assume that their logic would resemble our logic, that their concept of information would resemble our concept of information, that their reasons for communicating would bear some resemblance to our reasons for communicating, are these assumptions justified, or are we committing a profound error of imagination, projecting our own cognitive architecture onto beings who might think in ways so different from ours that the word thinking does not even apply? The question cuts deep, and the answer is not as uncertain as you might expect. On Earth, evolution has performed a vast experiment in the diversity of intelligence. There are roughly 8.7 million species on this planet, and many of them display some form of what we would recognize as cognitive ability, the capacity to learn from experience, to solve novel problems, to communicate with others of their kind. Octopuses can open jars and navigate mazes. Crows can fashion tools and plan for the future. Dolphins can recognize themselves in mirrors and understand grammatical structure in artificial languages. Elephants mourn their dead and can cooperate in complex tasks. But here is the crucial observation. Despite this extraordinary diversity of cognitive strategies and neural architectures, certain solutions appear again and again. Eyes have evolved independently in more than 40 separate lineages. Not because there is only one way to detect light. There are many, from the simple eye spots of flatworms to the compound eyes of insects to the camera eyes of vertebrates and cephalopods, but because the problem of light detection is universal and the space of effective solutions is finite, evolution, when faced with the same challenge in different lineages, converges on similar answers. This phenomenon, convergent evolution, is one of the most powerful patterns in biology. Flight has evolved independently at least 4 times in insects, pterosaurs, birds, and bats. Echolocation has evolved independently in bats and dolphins. The streamlined body shape of fast-swimming predators has evolved independently in sharks, dolphins, ichthyosaurs, and tuna. The camera eye, with a lens that focuses light on a retina, has evolved independently in vertebrates and cephalopods, producing organs so similar in structure that they were once thought to be evidence of common ancestry. They are not, they are evidence of convergence. The argument for convergence in intelligence is an extension of this biological pattern. The reasoning goes like this. Intelligence, the capacity for flexible, adaptive information processing, is a solution to a specific set of environmental challenges. These challenges are not unique to Earth. They arise on any planet with a complex changing environment where the optimal behavior cannot be hardwired in advance. The space of effective solutions to these challenges is finite, just as the space of effective solutions to the challenge of light detection is finite. And so, just as eyes have evolved independently dozens of times on Earth, intelligence might evolve independently on many worlds, and it might converge on similar fundamental principles. This does not mean alien minds would be like human minds in detail. The sensory modalities might be different: sonar instead of vision, chemical analysis instead of hearing, sensitivity to magnetic fields or electric current. The neural substrate might be radically different, not neurons but something else entirely, some alien information processing architecture that we have not imagined. The emotional landscape, if any, might bear no resemblance to our own. But at the level of basic logic and mathematics there would be common ground, not because logic and mathematics are human inventions, but because they are discoveries, descriptions of patterns that exist in the structure of reality itself. The laws of physics are the same everywhere in the universe. The integers are the same everywhere. The ratio of a circle's circumference to its diameter is the same everywhere. Any civilization that develops technology must have discovered these things, because you cannot build a bridge or smelt a metal or navigate by the stars without understanding them. This is why mathematics is the lingua franca of SETI. It is not that we expect alien civilizations to speak our language or to think in our conceptual categories. or to share our values and aesthetics. It is that we expect them to have discovered the same mathematical truths we have discovered, because those truths are woven into the fabric of the universe and cannot be missed by any sufficiently curious mind. A sequence of prime numbers 2, 3, 5, 7, 11, 13 is the same sequence on every planet in every galaxy. No natural process produces it. If you receive a signal consisting of pulses grouped in prime number patterns, you know with absolute certainty that the signal is artificial. You know that someone somewhere understands mathematics, and if they understand mathematics, then you have a starting point for communication, a thin, fragile, but real bridge across the abyss. Whether that bridge can be extended, whether the shared foundation of mathematics can support the weight of more complex ideas of science and history and art, is an open question. It might take decades or centuries to decode an alien message, even with the most powerful computers and the most brilliant cryptanalysts. Or it might be surprisingly easy if the message is designed by its creators to be self-teaching, starting with simple mathematical concepts and building up step by step to more complex ones, a primer, a cosmic Rosetta Stone. But all of this is premature. Before we can decode a message, we have to receive one. Before we can receive one, we have to build the instruments. Before we can build the instruments, we have to understand what we are looking for. And before we can understand what we are looking for, we have to grapple with the deepest question of all: what do we expect to find? The honest answer is, we do not know. And this is perhaps the most important thing about the search for extraterrestrial intelligence. It is a search into genuine, irreducible, magnificent ignorance. We do not know what we will find. We do not know whether there is anything to find. We do not know what the consequences of finding something would be, or how our civilization would respond, or whether the response would be wise or catastrophic. We are sailing into the unknown in the most literal sense imaginable. But we are also sailing into the unknown with tools, with mathematics and physics and engineering, with telescopes and computers and algorithms, with the accumulated knowledge of centuries of scientific inquiry, which has taught us how to ask questions of nature and how to interpret the answers. We are not helpless, we are not blind, we are just early. We are at the very beginning of a search that, if it succeeds, will be the most important discovery in the history of our species, and if it fails, will still have taught us something profound about the universe and our place in it. The cold in the Tonka Valley has a particular quality in the deepest part of winter. It is not merely the absence of heat, it is a presence, an entity, something that wraps itself around you and presses against your skin like a physical force. The researchers who work at the TAIGA array during the winter observing season dress in layers so thick they can barely move, and they venture outside only when necessary, scurrying between the heated control building and the outlying detector stations like astronauts on a hostile planet, which in a sense they are. Inside the control building, the air is warm and the light is steady. Banks of computer monitors display the incoming data in real time, a continuous stream of events, each one a cosmic ray or a satellite or a noise pulse or, possibly, something else. Something that no one has seen before, something that might, if the analysis holds up, turn out to be the first confirmed detection of an artificial signal from beyond the solar system. The researcher sits in front of his screen, running his algorithms, sifting through the data, looking for the signature that he has spent years thinking about. A brief uniform flash of light arriving as a plane wave, illuminating all the detectors simultaneously, with no spatial structure, no spreading pool, no expanding ring, just a single instantaneous pulse from somewhere beyond the atmosphere. He knows the odds are against him. He knows that most of what he finds will be satellites or cosmic ray coincidences or instrument artifacts. He knows that even if he finds a promising candidate, the statistical threshold for claiming a discovery is brutally high, and the scientific community will demand extraordinary evidence before accepting an extraordinary claim. He knows all of this, and he does the work anyway, because the question matters, because the answer, if it comes, will change everything, and because someone has to look. There is a famous thought experiment in the philosophy of science called the black swan problem. For centuries, Europeans believed that all swans were white. Every swan anyone had ever seen was white. The statement, "all swans are white," was supported by thousands of observations and no counterexamples. It was, as far as anyone could tell, an established fact. Then, in 1697, a Dutch expedition to Western Australia discovered black swans, thousands of them, entire flocks of swans that were not white but black, as though someone had dipped them in ink. In an instant, a belief that had been held with absolute confidence for centuries was overturned, not by argument, not by logic, but by a single observation. One black swan was all it took. The search for extraterrestrial intelligence is, in essence, a search for a black swan. We believe, most of us, most of the time, in our gut, if not in our intellect, that we are alone. Every observation supports this belief. Every SETI search that has returned a null result confirms it. The statement, "we are alone in the galaxy," is consistent with all available data, but all available data is not the same as all possible data. We have searched only a tiny fraction of the sky, in a tiny fraction of the electromagnetic spectrum, with instruments that are optimized for a type of signal that may not exist. Our failure to find extraterrestrial intelligence tells us very little about whether it is there, because our search has been so limited that even a galaxy teeming with civilizations might easily escape our notice. One detection would change everything, one confirmed signal, one black swan, and the belief that has held for all of human history, the belief that we are alone, would be overturned in an instant. In the fields of signal processing and information theory, there is a quantity called the signal-to-noise ratio. It describes the relationship between the strength of the signal you are looking for and the strength of the background noise against which you must find it. A high signal-to-noise ratio means the signal is easy to detect. It stands out clearly against the noise, like a shout in a quiet room. A low signal-to-noise ratio means the signal is buried in noise, like a whisper at a rock concert. The search for extraterrestrial intelligence has the lowest signal-to-noise ratio of any scientific endeavor ever attempted. The signal, if it exists, is unimaginably faint. The noise from cosmic sources, from terrestrial interference, from the instruments themselves is enormous, and the parameter space to be searched, the range of possible frequencies, directions, signal types, and arrival times is effectively infinite. And yet, there is a reason we keep searching. There is a reason that despite 60 years of null results, despite chronic underfunding, despite institutional skepticism and political ridicule, a small but dedicated community of scientists continues to point telescopes at the sky and listen. The reason is not stubbornness, though stubbornness helps. The reason is not faith, though perhaps something like faith is involved. The reason is that the expected value of the search, the potential payoff multiplied by the probability of success, is so large that even a very small probability of success makes the effort worthwhile. Consider the arithmetic. The probability of detecting an extraterrestrial signal in any given search is unknown, but even the most pessimistic estimates place it well above zero. Let us say, for the sake of argument, that the probability is 1 in a million. 1 in a million is very small. It means that if you conduct 1 million searches, you should expect to succeed about once. Now consider the payoff. If we do detect a signal, the consequences are, there is no other word for it, civilizational. It would transform our understanding of the universe and our place in it. It would resolve one way or another the question of whether the singularity is survivable. It would potentially give us access to information of incalculable scientific and practical value. It would be the most important event in the history of our species. What is the dollar value of the most important event in the history of our species? It is a question that does not have a meaningful answer, but you can appreciate the general shape of the arithmetic. Even if the probability of success is very small, the expected payoff is very large, and the cost of the search is very modest. By any rational calculation, SETI is one of the best investments that our civilization can make, and the probability of success may not be as small as the pessimists assume. The Drake equation, for all its uncertainties, suggests that there could be anywhere from a handful to thousands of communicating civilizations in the galaxy. The galactic cultural field model, if it is correct, predicts that the galaxy may be saturated with information from civilizations that have survived their singularities. The observation of Oumuamua hints tentatively, ambiguously, but genuinely at the existence of artifacts from other technological civilizations. None of this is proof, but all of it points in the same direction, toward a galaxy that is not empty, not silent, but full of whispers that we have not yet learned to hear. The Tunka Valley in winter, -40 degrees, a field of photomultiplier tubes pointed at a sky so dark and clear that the Milky Way looks close enough to touch. Inside a heated building, a researcher runs his code. The data streams in, event after event, flash after flash, most of them mundane, all of them interesting, each one a tiny piece of evidence in the largest and most consequential search in human history. He does not know whether he will find anything. Nobody does. That is the nature of the search. You look because the question demands an answer, and the only way to get an answer is to look. You look because the stakes are too high not to. You look because you are human, and humans are the kind of creatures who look, who build telescopes and point them at the sky, who send messages into the void and listen for an answer, who wonder and hope and refuse to stop wondering. The universe is 13.8 billion years old. The Milky Way contains somewhere around 400 billion stars, and most of those stars have planets, and billions of those planets are rocky worlds orbiting in the habitable zones of their parent stars, warmed by sunlight and probably blessed with liquid water. On at least one of those worlds, life arose and evolution produced creatures that learned to write and calculate and build machines and ask questions about the nature of their own existence. Whether this happened once or many times is the question, the biggest question that science has ever asked. And the answer is out there. It is encoded in the light and radio waves that fill the space between stars, or it is encoded in the silence, in the absence of signals, the emptiness of the void, the vast galactic quiet that might mean we are alone, or might mean we have not yet learned to listen. Either way, the answer exists. It is a fact about the universe, waiting to be discovered, indifferent to our hopes and fears and assumptions. There is something deeply humbling about this, and something deeply exciting. Humbling because it reminds us that the universe does not care about us. It does not care whether we find the answer or not, whether we survive our singularity or not, whether we ever develop the wisdom to match our technology. The universe simply is, and it will go on being long after we are gone, with or without us. And exciting because the search is still young, because we have barely begun, because the instruments we need are within our reach, and the data is accumulating, and every year brings new capabilities and new ideas and new reasons to keep looking. Because the question is so big and so important that even asking it feels like an achievement, and answering it either way would be the crowning accomplishment of a species that emerged from the African savanna less than a heartbeat ago, in cosmic terms, and has already begun to explore the universe. You are part of this story. You are alive at the moment in history when the search is happening, when the question is being asked, when the instruments are being built, and the data is being analyzed, and the first tentative, ambiguous, tantalizingly inconclusive results are beginning to trickle in. You will not always be alive. The window of your existence is brief and precious. And during that window, this species, your species, is reaching out into the dark, listening for a voice, hoping for a sign, searching for the answer to a question that has haunted every human being who has ever looked up at the night sky and wondered, are we alone? The honest answer right now today is we do not know. But we are looking with everything we have. And the fact that we are looking, the fact that we are the kind of creatures who would look, may itself be the most important thing about us. The stars do not care, the galaxies do not care, the vast, cold, beautiful, indifferent universe does not care. But we care enough to ask the question, we care enough to build the instruments. We care enough to sit in a frozen Siberian valley at -40 degrees and watch the sky for a flash of light that might, just might, tell us that we are not alone. And maybe that is enough. Maybe the searching is its own reward. Maybe the question is more important than the answer, but I hope we find the answer anyway. I hope that someday, maybe this year, maybe in a decade, maybe in a century, a signal will arrive from the deep sky, unmistakably artificial, undeniably real, carrying with it the proof that we have been looking for since the first human being looked up at the first clear night sky and felt the weight of all those stars pressing down. Until then, we listen. The photomultipliers watch the sky, the algorithms sift the data, the cold wind blows across the Tunka Valley, and the Milky Way pours its river of light across the darkness overhead. And somewhere in that river, somewhere among those 400 billion stars, there might be someone looking back. The search continues. There is a late-night quality to this kind of thinking, a sense of standing at the edge of something vast and unknown, peering into the dark and feeling both very small and very lucky to be alive. It is the same feeling you get when you lie on your back in an open field far from city lights and let your eyes adjust, and the sky opens up above you like a dome of diamonds, and for a moment, just a moment, you forget about everything terrestrial and become a point of consciousness floating in the immensity of space. And in that moment, the question does not feel academic. It does not feel like a problem in astrophysics or a topic for a seminar or a subject for a grant proposal. It feels personal, intimate, urgent. It feels like the most important thing you have ever thought about. And it is, because the answer, whatever it is, will define the meaning of human existence in a way that nothing else can. If we are alone, then we are the universe's only chance to know itself. Every human life, every act of creation, every moment of joy or sorrow or wonder is infinitely precious because there is no one else, no one to share the burden, no one to carry the torch if we drop it. We are it, the sole bearers of consciousness in a cosmos that is otherwise blind and deaf and dumb. The weight of that responsibility is almost unbearable, and the beauty of it is almost too much to comprehend. And if we are not alone, if the galaxy is populated with minds, with civilizations, with beings who think and dream and build and wonder, then the meaning shifts. But it does not diminish, it expands. We are not alone. We are part of something larger than ourselves, part of a community that spans the stars, part of a story that began long before we were born and will continue long after we are gone. And our chapter in that story, the chapter of the strange, brilliant, violent, creative, reckless, hopeful, doomed, and possibly salvageable species called Homo sapiens, is just beginning. Either way, the sky is full of meaning. Either way, the search matters. Either way, the question is worth asking and the answer is worth pursuing, no matter how long it takes or how hard it is to find. And somewhere tonight, in a frozen valley in Siberia, a single researcher sits in front of a screen, running his algorithms, watching for a flash of light. -40 degrees outside, the stars are very bright, the detectors are recording, the data is streaming in. He does not know what he will find, neither do you, neither does anyone, but the search goes on.